This is example 1. It says find e to the 5th power and also find e to the negative 1.75. E is a mathematical constant equal to 2.71828, and this goes on forever without repeating. Very similar to pi. Pi is 3.14159. Goes on forever without repeating. We use the letter E. The constant is named after a mathematician named Euler, and so we use E in honor of him. And so your calculator probably has an E button on it. I'm certain that it does. And so my calculator, I have an LN button, which stands for natural logarithm, which we'll cover in just a few moments. And if I press my second button and then press my LN button, I get an e to the x. And so to find e to the 5th, I'll press second LN button, which gives me e to some power, and I'll type in 5. So I'm taking e to the 5th power. I press equals, and I get 148.413. 148.413. I can do the same thing second, e to the x, negative 1.75. And so e to the negative 1.75 power is 173.774. 173.774. This is example 2. It says find the natural logarithm, abbreviated LN, of 4350. And so the natural logarithm means that we are taking the log where the base is e, Euler's number, and we're taking the log base e of 4350. And so on your calculator, where you see your LN button, that means the natural logarithm. And so we'll just type in LN, and then type in 4350, and press equals, and we get 8.378. So the natural logarithm of 4350 is 8.378. And so if we look at this equation, that the natural logarithm of 4350 is equal to 8.378, we can rewrite this in an exponential form where the base is e, the exponent is 8.378, and this is going to be equal to 4,350. And we can check our answer by doing that. If I do e to the x and I do 8.378, you can see I get 4,350.2, and that's because I rounded this number off. My calculator is in engineering mode, so this says 4.350 times 10 to the 3rd power, which is 4,350. This is example 3. It says given that the natural logarithm of x is 5.468, find x. And so again, natural logarithm means that the base is e. I could rewrite this just to help be clear that we're taking log where the base is e of x, and this is supposed to be equal to 5.468. We can rewrite this in exponential form where e is the base. 5.468 is the exponent, and this will be equal to x. And so we've solved the equation for x. If we take e to the 5.468 power, we will find x. And so that's what I'll do. I'll take e to the x, e to the 5.468 power, and oops, try that again, e to the 5.468 power, and we get 237 roughly. 237. We've seen this formula before, y equals a times the quantity 1 plus r to the nth power. This is an interest formula where a is the original amount, r is the rate at which something is growing, and n is the amount of time that passes. Now when we talked about this formula, this dealt with interest or a growth rate being compounded every so often, say once a year, or possibly once a month, or once a day, or once a week. Now if we want our interest to compound continually all the time, we'll use this formula where y, the new amount, is equal to a, the original amount, times e, which is Euler's number, to the rn power. And so what this formula accounts for is, say you have money invested in a bank account, a savings account, and you're earning interest. if your interest was to be compounded all the time, this is the formula we would use. And so it's saying that your money is all the time getting a very small percentage of growth, and it does that all the time. And so all the time your amount is growing, and all the time when we apply more interest to your amount, the amount is larger now, and so the rate of return on that amount is also growing all the time. And so this is going to yield the maximum amount of growth for an investment. So example 4 says that Joan invests $1,000 at 7.75% compounded continuously. So the compounded continuously tells us that we want to use this new formula. How much money will she have in the account after 5 years? And so we'll plug these numbers into the formula. Y, that's the amount that she'll have after 5 years, will be equal to 1,000, which is the original amount, times e to the r, which is the rate, and we need this to be written as a decimal. And so 7.75% is 7.75%, and as a decimal that will be 0.0775. We have to make sure that we use the decimal form, 0.0775, that's the interest rate, and n is the amount of time that's going to pass, is 5 years. Okay. And so you should work out the exponent first, right? Multiply these two numbers, figure out what the exponent is, and then raise e to that power, and then multiply by 1,000. So y will be equal to 1,000 times e to the, and I'll work out the exponent. We have 0.0775 times 5, and, well, let me put my calculator in normal mode. That's going to be 0.3875. 0.3875. And now we want to raise e to that power. So second e to the x, 0.3875. And we get y is equal to 1,000 times e to this power is 1.4733. Okay, last step will be to multiply. And so you can see what we're saying is that after 5 years, your initial investment will have grown by 47%. The 1 is your original amount, your 1,000. Right, so 1 times 1,000 is your original amount, 1,000. And the 0.4733 times your 1,000 is the amount that it has grown by. And so when we multiply by 1.4733, that's going to be the sum of your original amount and then also the amount of growth. So this is how much you will have in your savings account or your investment after that time has passed. So we'll take 1,000 and we'll multiply by 1.4733, and we get 1,473. So at this interest rate, after 5 years, and an initial investment of $1,000, after 5 years you'll have $1,473. And again, that's the original $1,000 that you had, plus another $473. That's what you've earned. This is example 5. It says a city has a population of 850,000, and a nearby suburb has a population of 65,000. Studies have determined that the city will lose population at a rate of 2%, while the suburb will gain population at the rate of 4%. Find the population of each in 5 years. And so, two different situations here, a city and a suburb. The city is losing population by 2% per year, and the suburb is gaining population by 4% per year. So the rate of growth of the city is negative because it's losing population, whereas the rate of the suburb is positive because it's growing. Now, the population loss of the city does not all occur on, the first day of the year, right? People are leaving the city all the time. It could be right now, it could be a few minutes from now, it could be an hour from now, it could be a week from now. Right? Same thing with the growth of the suburb. It doesn't all happen at once. That whole 4% does not all of a sudden just move in all on the same day. It's happening all the time, all throughout the year. And so that means we want to use the continuously growing formula, where we have y is equal to a times e to the rn power. So that's the formula that we're going to use. We'll do the city first. The population y after 5 years, will be equal to the initial population, 850,000, that's A, times e to the r, and r we need to make sure that it's negative, first of all. And we also need this to be in the form of a decimal rather than a percentage, so negative 0.02, that's 2%. And then times n, which is the amount of time that has passed. And so, again, I would work out the exponent first. If you want to be very careful, work out the exponent first. Negative 0.02 times 5 is negative 0.1, so y equals 850,000 times e to the negative 0.1 power. And now I would take e to this power, and so second e to the x, negative 0.1. And so we get y is equal to 850,000 times 0.9048. And you can see that this number is less than 1. And that's because the exponent was negative. And so remember that when the exponent is negative, that is the same thing as 1 divided by e to the positive 0.1 power. And so that means that we're getting a number less than 1. Because it's a fraction, the denominator is going to be larger than 1. And so this will work out to a number that's less than 1. And that, again, is the indication that the population is declining. And so what this formula is saying is that the population will only be about 90.48% of what it currently is after 5 years. And so what is that value? Well, we have 850,000, and we're going to multiply by 0.9048. And so after 5 years, we expect the population to be 769,000. Now we'll work out the problem for the suburb. Same problem, y equals 65,000 times e to the r, which again I need this to be in a decimal form instead of a percentage, so 0.04, times the time that has passed, which is 5 years. And so 65,000 times e, work out the exponent first. We have 0.04 times 5, which is 0.2. The exponent will be 0.2. And so now we'll work out e to the 0.2 power. E to the 0.2 power, which is 1.221. 1.221. And now we can multiply. So the population after 5 years will be 65,000 times 1.221, which is 79,365. 79,365. And again, you can tell that because this number is greater than 1, the population grew. And because this number was less than 1, the population declined. And again, this number was less than 1 because the exponent was negative. This one was greater than 1 because this exponent was positive. This is example 6. It says a culture contains 100,000 bacteria. It grows at a rate of 15% per hour. How many bacteria will there be in 12 hours? And so again, the bacteria, they're dividing all the time, and every time they divide, there are more that are now available to divide again. So they're growing continuously. And so we want to make sure that we use the continuous growth formula, y equals a times e to the rn power. And so y will equal a, the initial amount, 100,000, times e to the r, and again we want the rate to be a decimal, 0.15. So that's 15%, times the amount of time that has passed, is 12 hours. And so work out the exponent first. We'll take 0.15 times 12, and we'll have y equals 100,000 times e to the 1.8 power. Now we'll work out e to the 1.8 power. So e to the 1.8 power is 6.05. So it's going to be 100,000 times 6.05 and 0, because that 49 rounds up to a 50. And now we'll multiply 100,000 times 6.05, and we get 605,000. So you can see at continuous growth at 15% per hour, after 12 hours the population of the bacteria is more than 6 times the original population. This is example 7. They start by giving us a formula that I is equal to 2.4 times e to the negative 4.0 t power. This is an equation dealing with electrical circuits, usually circuits that have either capacitors or inductors in them. And so if you've had any of my electrical engineering courses, you might be familiar with these types of formulas already. And so this formula is telling us how much current is flowing in the circuit after a given amount of time. They want us to find the current after 0.35 seconds, right? And so that's t, they've given us that value. So we can find the instantaneous current, which is I. That'll be equal to 2.4 times e to the negative 4.0, where t is 0.35. And so we'll do the same thing that we did before. Work out the exponent first. So negative 4 times 0.35, and we get negative 1.4. Now work out e to that power. So we'll take e to the negative 1.4 power, and we get 0.247. Now we can multiply. So we take 2.4 times 0.247, and we get 0.593. 0.593. The answer here will be in amps. So I is the instantaneous current in the electrical circuit, and that is measured in amps. So you know that your calculator has a log button, which is log base 10, and an ln button, which is log base e. But what about other bases? If you want to use your calculator to find log, let's say for example, log base 5 of, how about 50? Log base 5 of 50. What is log base 5 of 50? Well, we could say that this is equal to some number that we don't know yet, x. We could rewrite this as an exponential. 5 to the x power is equal to 50. And the question becomes, well, what is x, right? So is it 2? Well, 5 squared is 25, so it's not 2. Is it 3? Well, 5 to the third power is 125, so it's not 3. It's somewhere between 2 and 3, right? X is somewhere between 2 and 3. X will be greater than 2, but less than 3. Well, what is it exactly? It's a decimal. And so consider that u is equal to log base b of x, where b is some base, right? Some base other than 10 or e. And so if we rewrite this as an exponential, this is b to the u power is equal to x. B to the u power is equal to x. Now if we take the logarithm of both sides of the equation, which I'm allowed to do, for example, let's say that 5 minus 2 equals x. I'm allowed to add 2 to both sides, right? Whatever I do to one side, I can do to the other. And so as long as I do the same thing to both sides of the equation, I'm allowed to do that. And so I'm allowed to do the same thing to both sides of this equation as well. So I can take the logarithm, let's say base a, okay, some new base, not b, but some new base. Log base a of b to the u power will be equal to log base a of x. Now a here is going to be a logarithm with a base that our calculator can handle, such as 10 or e. And it doesn't matter which one it is as long as it's the same. And so now we can apply some of the rules of logarithms. E is the exponent. We can bring that out as a multiplier. So this becomes u log base a of b is equal to log base a of x. And so u is being multiplied. We can divide both sides of the equation by log base a of b. It cancels over here, and we get u is equal to log base a of x divided by log base a of b. Now remember what u was equal to originally, the logarithm with a base other than 10 or e, right? B is some other number other than 10 or e. So let me plug that back in for u. U is log base b of x, and this is going to be equal to log base a of x divided by log base a of b. So what this formula says is that if we're trying to take the logarithm with a base that we're not sure of, it's not 10 and it's not e, we can find that value by taking the log base a, such as 10, of x, where x is still the same value, divided by log base a of b, where b was the original base. So what this says is we can take log base 10 of the argument of a logarithm and log base 10 of the base of a logarithm and divide them, and that will give us the same answer as finding log base b of x. So for example, let's look at log base 5 of 50. Now my calculator, and yours may have this as well, my calculator has a math button, and if you have a TI-83 like this, or 84 or something like that, you may have this as well. If I press the math button, I get a menu, and I can arrow down, and I can find a function that says log base. Log base. And so log base allows me to enter some other base, like 5, and then enter the argument, which is 50, and press equals. And we can see that x here is going to be equal to 2.431. So in this example, we said it was between 2 and 3, and it is. It's going to be 2.431. 2.431. Right? Some calculators will do that. Yours may not. If it doesn't, that's okay. We can find the answer using this method. And so we wanted to find the log base 5 of 50. And this is going to be equal to log base 10, let's say, log base 10, right, or the common logarithm of x, where x is the argument, which is going to be 50, divided by log base 10 of b, which was the original base, or 5. Okay, and so log base 5 of 50 will be equal to, and I'll type this into my calculator, the common logarithm of 50, close parentheses, divided by the common logarithm of 5, close parentheses. And what do I get? 2.431. Same answer we had before. 2.431. Now, it didn't matter if I used log base 10 or if I used the natural logarithm, it's going to work out the same way. So let's try the natural log of 50 divided by the natural log of 5. And so I'll try that. I'll take the natural log of 50, close parentheses, divided by the natural log of 5, close parentheses, equals, and I still get 2.431. 2.431. Right, same answer that we got before. And so when you use this formula, it doesn't matter what the base is. It can be any base, as a matter of fact. But your calculator has capabilities for base 10 or base e. So those are the ones you're going to use. It doesn't matter which one you use, whether it's common log or the natural log, as long as you use the same log both times, right? So you can't use log 10 and then natural log, or natural log and then log 10. That has to be the same both times. This is example 8. It says find log base 3 of 370. And so again, your calculator may not have the capability to find log base 3 of a number. And so we'll need to use our formula that we just discovered. And so the log base 3 of 370 will be equal to log base a, and again it doesn't matter if you use natural log or the common log, I'll use the natural log, of x, where x was the original argument, 370, divided by the natural log of the original base, 3. Right, so the argument is always in the numerator, the base is always in the denominator. And so log base 3 of 370 will be equal to, and now I can use my calculator, because I have a natural log button, natural log of 370, close parentheses, divided by natural log of 3, close parentheses, and the answer is 5.383. 5.383. And so we can check our answer, because I can rewrite this as an exponential now. This is the base is 3. The exponent is supposed to be 5.383. And this should be equal to 370. Now I rounded my answer, so it'll be close, but not exact. And so we can test that. 3 to the 5.383 power, and we get 370.1, or close enough to 370. And again, that's because of my rounding error.